Okay. All right. So we'll have a little bit of recording here. Oh, I just got to think about last week. Hope we didn't scare Scott away because he wasn't real happy about the recording, or not happy, but he didn't really like it. But I noticed there was over 50 views of last week's recording. So I go, oh, well, I'm glad I did. I think it was you, Daniel, said, go ahead and record it, please. Could have been Anthony, but.
I didn't say that, but I'm definitely appreciative of it.
Okay. But somebody did, and I that wasn't in my game plan, but I was really glad I did afterwards. And once I post them and sent it out this week when I was getting ready, I noticed 50 views, and I was like, oh, okay, it must been somewhat helpful somewhere along the line. All right, so back to your question here. All right, so number 20, what is this? 24, okay.
27.
I'm sorry, yeah. I wrote it right, said it wrong. So chapter 24, number 27, and scan down here to and 27. It says, consider a long cylindrical charge distribution of radius capital R and of uniform charge density rho. Find the electric field a distance r where r is less than capital R. So they're talking about inside. So I'll start by saying, if I were to draw kind of a cylinder looking thing and trying to make it three-dimensional, maybe I'd do something like that. This would be capital R. And they said there's a bunch of charge spread out. Let me just read it and make sure I read it wrong. I mean, I read it right. I didn't read it wrong. Where did 27 go? There we go. Okay, consider, so it is a cylinder, and there it is, charge density rho. So if there is charges spread out with inside of it and all over, we know it's not a conductor, because we know conductors, all the charges are on the surface. And we also know the electric fields are zero inside. Okay. And that's not what we have here. Okay. Then they say, find the electric field on the inside here. So maybe a change of color could help. But I'm going to draw a Gaussian surface that has this kind of cylinder shape. The Gaussian surface I'm going to draw has a length of L and a radius of what I'll call little r. Okay. And of course, the key to this question when I read it and what was going through my mind is I said, find the electric field. And we have learned two ways of getting the electric field. Last chapter was Coulomb's law, and this chapter is Gauss's law. So the whole point here, if you didn't quite catch the bigger picture, was to give you these two techniques here at the beginning as we try to move forward and understand electricity and electronics and magnetism before the semester's over. And so this beginning part is just what is the electric field and how do we figure out its value? And these are our two techniques. And so this chapter this week is all about Gauss's law. So I'll write Gauss's law here, E dot dA, and charge inside over epsilon naught. Okay. And Gauss's law, as I was been saying a couple other times today, is you gotta visualize a lot of this. You could really simplify this with a good Gaussian surface. you could change this integral into something else that it's no longer an integral. And so it looks scary. You know, I bet if you showed your friends this equation, say, here's what I'm doing in our class, they might get a little scared. Oh, whoa, that looks hard. Okay. But this is the a visual solution, I guess is the word I'm looking for. All right, so let me go ahead and look at this Gaussian surface that's buried inside of the real physical object and say, if I take the dot product first, and if I do those symmetry arguments that you heard me do in the video lecture, then we can simplify this integral incredibly. The first thing in the argument is that somewhere on the surface, anywhere on the surface of this mathematical surface, so it's not really a cut, it's not a physical surface. I didn't really install a piece of aluminum or something inside of there. But I mathematically sliced it and said, okay, on that surface, all the charge distribution, when I'm say at this point, would look the same as if I'm at this point. Now, of course, this has to be a really tall rod, so tall that we call it infinity. So here, there's a bunch of charges above me and a bunch of charges below me. Same thing, there's just as many above me as below me. And then, of course, around the circle, they would look the same. There'd be some towards the center and some towards my back. Anyways, because it's that symmetry argument that allows us to say that the electric field, whatever its value is, would be a constant, and I can pull it out. That's the big piece of Gauss's law. Or the other big piece of Gauss's law is we know something about this angle. And in this case, we know it's 0 degrees. We know that because we know the electric field would be along any line of symmetry. And you're shaking your head, yes, and I'll just do a cross-sectional picture like I was showing in an earlier Zoom, that if you have a round, and so cross-section, a circular here, and I kind of put my hand on top of it and I flip it. Imagine drawing a line through it, a line of symmetry. Flip.
Oh yeah, with the pencil.
Yeah, you would get the same charges. So if I did that with a pen pointing this way, it would be the same direction. A pen pointing any other direction, when I flip it, points in a different direction. So since when I flip it, the charge distribution is the same, I have to have a direction that would be in such a way that when I flip it, it's still in the same direction. And so that's only along a line of symmetry. So that tells me the electric field is also radially out. And I say also because the area vector is radially out. So both of these are in the same direction, radially outward, and that's where that 0 comes in. And this is what I was saying. We've taken what looked like a hard calculus problem because it's got a dot product. First, we got rid of the dot product. Then we pulled that in front of it. We got rid of the cosine of theta. And then we've got something else. Again, we won't even do the integral. We'll just say this is the area of the Gaussian surface. That's exactly what this is saying. This is saying summation of a bunch of areas. You add up a bunch of areas, you're going to get the area of this cylinder. And so now I can just come to kind of a visual effect and say, okay, here's my cylinder. And so if I take this cylinder and I want to know its surface area, maybe it's best to visualizing unrolling it. And this length would be the circumference, and this length would be what I called L. It's length here. So the area would be the 2 pi r and L. So that's the left-hand side of the equation. The right-hand side of the equation is going to be a little bit harder. I will start with just the constant left alone, the permittivity of free space. But this is where I'm going to say, let's come back up to the picture. I want to know how much charge is inside this Gaussian surface, not the whole thing. In fact, there's technically an infinite amount of charge because this cylinder goes infinitely up and infinitely down. So if this had meant the charge on the cylinder, I have put in infinity, but that's not what it means.
Is that
This
just charge density times volume.
It is in this case, and I'm glad you asked that. I just want to prepare you for some of the harder ones. So let me come up here and say, here's how I would think about the charge on the inside. I would say it's the sum of all the charges. And since density is dq over volume, I could replace that dq with the density times the volume. And then if density is a constant, did you catch that? I'll say it again. If density is a constant, I can pull it out and get density times volume. Now, the reason I'm making a big deal out of that is
That's for
because
the
in this
conductor
problem,
problems, right? Sorry.
the density is a constant. But in the harder ones, near the
Yeah.
end, the two end problems, the density is not a constant. And so you got to go back to this step and leave it inside the integral. I think one of them, somebody had me doing it a little earlier, the density was A over R.
Yeah, that was 57. Yeah.
Yeah. So I did not pull it out in front, but the easier ones, and again, notice I'm saying easier because nothing's easy about it, but the easier ones are just algebra, and this calculus shows how the algebra, you just take density times volume. So since that's the type of problem this is, I will put, as you say, density times volume, okay? But I went through all that mumbo jumbo to hopefully help you on the harder ones where you can't just write the charge inside equal to that. Okay, but this one is a little bit easier. Okay, so now I've got the density and then the volume. Well, coming back to a cylinder, where's my cylinder? I'll wrap it up again. Here's my little cylinder. And kind of remembering from a math class, the volume is the area times the height of it. So this area down here would be pi r squared. And it would be little r because it's the volume of the Gaussian surface, and then the length L. And now I can simplify. An L cancels off. A pi cancels off. One of the r's cancel off. And let's see, I'm left with a density, an R, density R, and then the 2 from this side, and epsilon naught.
Sorry, I got here late, but I'm wondering why there's no flux going through the two circle ends, only on the surface.
Oh, yeah, okay. Okay, yeah, great question, because when you do, as you said, the flux, you've got to include everything, okay?
Also, the top and bottom just cancel out?
No, I wouldn't say it that way. I would say it this way, that if this is my surface, my argument from symmetry is that the electric field is going straight out that way. So no flux goes through that surface. Put in math terms, this angle would be 90 degrees. The electric field would go in the direction of my pen, that way. But the surface on the top would be pointing upward. That would be the dA.
Wait, why is it not going up?
I'm gonna draw a picture. You say it, do you mean the electric field?
Yeah, sure.
Yeah.
I was talking about the flux, but
Okay, so let me just draw the Gaussian surface, and so this would probably be the edges of that big charge. But if this is this line here, okay, let's just pick some point on the Gaussian surface, any point, let's say, and of course you're concerned about the top, so let me put a point that's probably about halfway out on the top. But where is my line of symmetry? You see, this horizontal line would be a line of symmetry. If I flipped it around here, this cylinder, which goes infinitely far down and infinitely far up, would look exactly the same. This is not a line of symmetry. If I were to try to flip it, see, right now, there is more charge to my right than my left. If I flip it, then this center line would be over here. This line would be further out. This line would be here. And now I would have a less charge to my right than my left. That would tell me the electric field does not point that way. That is not a line of symmetry.
Why do you care about the line of symmetry so much?
Oh, okay. Because as you are trying to do the math, you need to know this angle. This angle is the angle between the electric field and the area. And the electric field is always along a line of symmetry.
Oh, okay. I see.
So coming back to, I think maybe now finishing your problem, this would tell me this is a line of symmetry, so this is the electric field. And the area vector would be straight up, so there's the area vector. That's 90 degrees. And so maybe visually you could see that that would be no flux. And then hopefully also mathematically, you would put a 90 degrees here would give you 0.
Yeah.
And that's why I ignored, and I probably shouldn't have. I should have said the top would be 0, the bottom would be 0, and the only surface I should care about is the wraparound face.
Got it. Thank you. Oh, and
Yeah.
I have another question on number 29.
Okay. Oh, hold off on again. Can you shoot that into the chat? We'll come back to that. But I think where were we? I think Jonah was next. I don't think I've done Jonah this time.
Oh, okay.
Me?
Yeah, Jonah. Did somebody from 121 have a question? Oh, you're asking about the pizza one, yeah?
Yeah, somebody asked this before, I think, but I don't know if you got around to it, the scaling your percentages with pizza.
I did not get around to it. Are you asking about it?
Well, I was only saying that because I was wondering if someone else was going to ask it because I had a different question, but I also wanted to see that one get done. But so no, that's not my question. But mine's on adding vectors.
Adding vectors? Okay, well, let's do your adding vectors. And I want to do that pizza one, but I'm waiting for Bellikakov to come back in.
Well, if he's here right now, you could just do that one first and then you can do mine next.
Well, he's logged in. I see his name, but I think he's probably working on another problem. So that's why I said maybe we ought to do your vector one.
All right. Well,
I'd hate to do it for him to come back in and then miss it. Well, I guess I could do it again. Wouldn't be a big deal.
Well,
Let's
yeah,
do
we
your
could
vector
just do
one.
the vector. Okay.
Yeah.
So it says a plane flies a distance 82.3 kilometers in a direction
Excellent.
30. Sorry?
Yeah. I actually, let me go back to my notes. Somebody asked this actually 2 times in the session before. So if it'll be okay with you, I'm just going to, and tell me if I got the numbers right. There is a grid system and you're trying to find out the distance between 2 airplanes, right?
Oh, no. We did that one together with
Oh.
you and me, but this is a different
Okay.
one.
This is different. Okay, sorry, go ahead. I messed up.
Yeah. So a plane flies the distance 82.3 kilometers in a direction 30 degrees north of east. Actually, is sharing the screens on? Because I feel like it'd be
Oh,
easier.
let me do this. I think I can let you share once I stop sharing. So let me stop sharing. Let me go to, oh, there, all participants. Okay, yeah,
Okay.
if I did it right, you should be able to share your screen now.
Yeah. Okay. You should see it.
Okay. Excellent. Okay, so this says, let me get a clean piece of paper here. All right, so a plane flies 82.3 kilometers, direction of 30 degrees north of east. Then the plane flies 118 kilometers at a direction of 60 degrees north of east. At the end of the trip, the plane is at a distance c away from its starting location.
Yes.
Okay, I didn't see a question there. Are we just find c?
Yeah, we find C.
Okay. Yeah, I'm looking for a question mark. Okay, so big picture here is they're trying to teach you some mathematics. Oh, I lost your screen. Let's see.
Wait. I thought you were gonna put on your
Yeah, I am. Sorry. Let me just just to write down some numbers though.
Oh yeah. Do you need me to put it back on?
Yeah, if you put it back on, 30
Yeah.
degrees north of east. I think I read 82.3 kilometers. Then it went, this is the one I didn't remember, 118, 60 degrees north, and our job is to find C. All right. Okay, perfect. All right. Yeah, my apologies. I should have said, hold on here, because when I start sharing, it will kick you off.
No problem.
Okay, and then let me just go back to my screen monitoring. And it's like the little wheels spinning. Come on. There it goes. A little sluggish that time, but we're back. All right, so I'm back to my camera, and then there's the picture I drew while you were. Okay, so there's the kind of the picture I drew. Okay. Now, let me start with a picture on this picture I drew, because the point of this problem is to find this distance, C.
Right.
And keep in mind then that C has what I'll call a Y component, and then C also has an X component. And that means C squared would be how far does it go in the X direction and how far does it go in the Y direction, okay? A better notation than what I just did is C squared is equal how much in the X, and so this is called the X component of C. And then this is called the Y component of C. So that's the notation you might want to get used to.
Mm-hmm.
All right. Now, here's the other thing. How do we get the X component? And coming back to this picture, maybe you can see that if we took the X components of vector A and the X component of vector B, those two added together would give us the X component of C. And so the phrase I like to use is to get the x components, you got to put x's with x's. And the same logic in the y direction, and I'll put it on the picture, but this would be the vertical height for the a vector, so call it a sub y. And this would be the vertical height of the y component, so call it b sub y. And again, the phrase I like to use is to say puts y's with y's. All right. So let's start with this, and then we can put it in here to ultimately get our distance. All right, so let's go back and look at this vector A. This is its magnitude, and this is its adjacent component. I say the word adjacent, trying to trigger in your mind trigonometry, because cosine, so cosine of 30 degrees is the trig function that would give you the adjacent, and it would be over the hypotenuse. So that means the x component would be 82.3 times cosine of 30 degrees. So grabbing my calculator and first checking if I'm in degrees, good. I will go 82.3 and multiply it by cosine of 30 and get 71.3. That makes sense so far?
Yeah, no, this makes sense. I just, for some reason, he wrote down C equals A plus B, and that threw me off because he gave us A and B. So.
Oh, okay. Well, now wait a minute. You see all this mumbo jumbo I said about how we got to put X's together to get X's and Y's together with Y's?
Yeah. No, I understand why he wrote that down now after you showed me that.
Okay. But maybe I want to show you something else too. If it's got an arrowhead over it, we still write it as A plus B equals C, but we do not mean just take the magnitude of A and add it to the magnitude of B. What we mean by this is all of this more complicated mumbo jumbo.
Okay. All right. Yeah. So I see now. So just basically turn C into a large right triangle by solving AX and BX and AY and BY.
Exactly.
Okay.
Yeah. Good.
All right. That's good.
Yeah. Good. And I'm glad you see it, because it really helps, I think, to have a visual picture. One of the skills hopefully you'll develop as you go through 121 is, physics is physical, and seeing the physical picture really helps a long way.
Mm-hmm.
If you were hanging around for a little bit, I've done a lot with the 121 or 122 class and saying, hey, do you visualize this flux? Are you visualizing what direction it goes? So yeah, visualization is a good one, but
Right.
Sounds like you got the rest of it, but I just wanted you to be careful.
I do. Thank you for the help.
Okay, you bet. Okay, let's see. That was Jonah, who started off with the pizza problem, and we'll keep waiting on that pizza problem if need be. Other Jonah. Wait. No, that's Jonah again. Me. Kenny, are you still here? Kenny just
Seems
says
like
me.
Professor Folsom makes a lot of problems with food. I remember that from Physics 102. He made a lot of food problems.
Oh, really? Okay.
Yeah.
Okay.
Timmy's here.
Who's here?
Yep. So Yes, I had a question for number 29. I only have the question for A, so I just don't get why we don't use, since the R is smaller than A, why don't we just use the equation we learned from the class, you know?
I like what you're saying here. Repeat that here. Let me come back to the homework. Which number?
29.
29. Consider. Yeah. You can go ahead and use the one that was derived. Let's see. This is a sphere, so I think it was example number 3. If you just want to use the equations, because in example number 3, the author worked out both inside and outside. Right?
Example number 3.
This is a thin shell. I'm sorry. Example number 3 was solid.
Oh, this one is empty. That's why.
Yeah. See, the first part of it says, consider a thin spherical shell of radius 14. Mm-hmm. So the inside, the field would be 0.
Why would it be 0?
Well, do you want me to show you are both a picture or a mathematics?
Picture would be nice.
All right, I'll do picture. All right, I'll start there, and I can do math after that if you want. But here is kind of Gauss's argument. So you have this shell. So imagine that red line is charged, and it's hollow on the inside. And let's look at a point somewhere on the inside. Maybe I'll just pick right here. So, notice I'm not picking exactly in the center. I'm just picking some random point. And I want this point to represent any point in there. And what I'm going to do is, first of all, draw kind of a dotted line that would be an axis of symmetry. So it would go through the center of it. Then I want to draw 2 solid lines that cross at the same angle. Doesn't matter what that angle is. As long as they are equal on both sides of the line of symmetry. Okay. And the argument goes something like this, that.
Yeah, I remember.
Oh, you saw this one earlier?
Yeah, from the video. So
Oh, did I do it in the video too? Good.
Cancel out.
Yeah. So if I call this area 1 and area 2, those are exactly symmetric. I think those are easy to see that they cancel off. But if I call this over here 3 and this over here 4, that's not quite so easy to see. But it is easy to see that there's more charge at a further distance away than the charge over here at a short distance away. And since the electric field from last chapter, a point anyways, and that's how we would get the field by adding up all the points on here, changes with r squared, but area also changes with r squared. I would say that the fact that we're further away and the field is weaker by r squared is exactly made up by the fact that we got more charges because the area is greater by r squared.
Yeah, got
and
it.
So 3 and 4 cancel, and so inside it's 0.
Got it. Thank you. Thank you.
Sweet. Yeah, that's a fun statement. All right. Where was I in the chat room? For the 121 people, did unit of measurement, did you use area per time? Answer, years. I think you're talking, I don't know what other people did, but when I worked through this one, I got, first of all, I just did it in years, and it was such a small number in years, I eventually changed it to seconds and came up with 24 seconds. So that helps, Jonah. but I would think it wouldn't matter. They're both correct.
I don't know. I think it does matter, but maybe I just did the work wrong but I also tried years, so I probably just did the work wrong. But I did it along with you, which I ended up just doing. I ended up just doing my number, which was 10,200 times 1,000 squared, because you did the trick with the kilometers squared.
Yeah.
You did, k squared, m squared, then you crossed out the m squareds.
Yeah.
So then I ended up doing the 10,200 times 1,000 squared, and then, divided my left side with that number.
Yeah.
And ended up with some number that I don't have anymore, actually. It was like 7.5 something.
Okay,
e
yeah,
to the
I got
negative 7.
I put it on the screen here. This is what we did together. Yeah, 7.65 times 10 to the negative 7 years.
Yeah, so it's pretty close to that. So I thought that would be the right answer, but maybe I just wrote something down wrong. Maybe I just wrote that's why I was thinking it was the wrong unit, because I did it with you and it seemed right.
Okay, yeah, this is what I got.
Yeah.
What makes you think it's wrong?
Well, it says I'm wrong. It says
Oh.
It says here. Okay, here's what I got. I got 7.5196 e to the negative 7 years.
Say that number again. 7 point what?
5196.
Now you got 5-1. I got 6-5 here.
Yeah, but you also used 10,400 and I used 10,200.
Oh, did I write this down wrong?
No. Everyone gets different numbers. He has like a random number generator.
Oh.
Yeah.
Oh, I didn't know that.
So that's what I had for numbers, but
Well, let's see what I get. So 7,960. I'm assuming that one didn't change.
no, that one did change. I had 7,670.
Oh. 7,670 divided by 10,000. And you said your new number is 200.
Yes.
And then divided by 1,000 squared would, I got what you said. 7.52 to round it.
Mm-hmm.
Times 10 to the negative 7 years.
Yeah, that's why it's confusing me. I don't know what so I think it is the units, but definitely a little confusing.
So then if I did this, I would say go back and try that in seconds. That many years, I'm going to go 365 days. I suppose we could do 365 and a quarter for leap year. And I'll just do 365 here. That's how many days. 24 hours in a day. 60 minutes in an hour. And then finally 60 seconds. 23.7 seconds. I don't know, does the system you're using, is it flexible enough that you can put it in years or seconds, or does it have to be one or the other?
I don't think it's very flexible. Let me try though.
Okay. Because
it doesn't accept seconds.
That system is pretty precise.
I have a question. Did you actually type write out years? I know when I did Doug's 102 physics where he did the thing, you would have to type units as well.
Yeah, I did. He has a new thing now where you have to do $sign then the units in order for it to recognize it. Yeah, I know, because I took his 102 and I know we have to do that, but it's a different system this time around.
Yeah, no idea then.
So it was
you just made me realize I was trying to help you guys this year. I can help you well with the physics. I'm not sure I can help you with the technology. I'm not familiar with what system he's using.
Yeah, that's all right. At least I know I got the numbers wrong. So numbers right. So I could just talk to him about it.
Yeah. Good answer. Yeah.
Thank you.
You bet. You bet. All right, shall we finally do this pizza one?
Yes.
You're next on the list. Can you unmute, or is that the problem? You can unmute? You want to write the pizza question in here again? Oh, I see. You weren't asking the pizza one again. You were helping Jonah. And again, sorry if I'm butchering your name, but Belikov? I think, yeah, you're saying you was it in years for you. I hope he saw that. He's checked out now. All right, so I'll go to the next one here. 29A. Is that what we just did, or Timmy did do yours?
Yes, we just did it.
Okay. All right. I don't see anything more in the chat. 1, 2, 3. Are we down to 6 people? Cool. Only the smart people are left.
Oh, I want to give everybody a reminder. So this morning I was looking at my grades and I realized on the transcript, even I got my grades as a letter, but when it's saying how many points you earned, there was 0. I don't know if anyone's trying to transfer this semester or next semester, but just watch out your grade from last semester. It might be errors, just like mine.
Mm.
Yeah, my
They
final.
put in the wrong final grades?
Yeah, they give me the wrong final grades.
Whoa.
I guess I have a question, but it's not necessarily on the homework. Really, it's more about the class. I am doing chapter 24 problems right now, but I'll be honest, I have not finished 23. I've been trying to do a lot, but I work a fair amount. I was wondering, is it worse if it comes time to collect the homework? Is it worse to turn in some slightly incompleted homework if I, for whatever reason, can't? I know it's down the line. I'm thinking I'll be able to, but I know we have current chapters. Or is it better to wait until it's fully complete and then submit it? Like,
well, the homework, this is part of the reason I've set it up so that the homework is not actually due till the test day.
mhm.
Okay. So I would say keep working on them until test day,
Mhm.
and then turn in what you've done.
Okay.
I'm not sure hanging on to them after the test is worth it, because you should probably use that as a chance to kind of clean that slate and move forward. But but then again, on the other hand, if you want, so I guess I'd say it's up to you.
Okay.
Here's my plan: is just to have a due date, and then if student says, well, I really have still been working on, in chapter 23, by that time you would have had a long time to work on it, but
Mhm.
chapter 26 you wouldn't have had that much time to work on it. So if you
Mhm.
wanted to finish it up, and I will gladly extend the due date. There is nothing special about the due dates, and if you want to learn more, but I do think it's nice to kind of have that due date, and then if you were behind, you kind of start anew. Okay, now I'm not behind. Now I'm going to do it again. And if you turn in really anything that is 50% complete or more, I'm going to give you full credit. It's a value of just, did you do it? Did you put in an effort? Are you working towards that goal?
Okay. All right. Cool. That makes me feel a lot better because awesome. Cool. Because this whole online learning, I'm having to watch lectures like 2 times over and all that. So I'm like,
Yeah.
I want to make sure I don't really. Cool.
Yeah. So I would say this, that, probably what you're doing is great. Just keep doing it, turn it in, and you're going to get 100% on the homework. Your real grade, of course, is decided by how you do on the test.
Yeah.
That's 75% of your grade.
Mhm.
Labs are kind of the same thing. do them, turn them in, you're going to get 100%. So you should be getting about 100% on both the homeworks and the labs, and that's 25% of your grade.
Okay, cool. So just
Which is
make
why-
I
yeah,
do
that's, which
all
is why I
those-
tell students, if you want to get that A,
Mhm.
you don't have to get 90% or above on the test, because you're going to get 100% on the homeworks in the lab. So if you can just get 86% on the test, then together with this labs and homeworks that you've done 100%, your overall grade will calculate to 90%. You'll get an A.
Okay, awesome. Cool. That's the grade I'm going for. So that gives me
Okay.
more clarity.
And then, and just to complete that, the B is the same thing. If you could get 73% or higher on the test,
Mhm.
and you factor in 100% for doing the homeworks and the labs,
Mhm.
that would get you up to overall an 80%. And that's your B.
Awesome.
Much nicer than my previous calc classes, because our
Yeah.
grade was only
Thanks, Mike.
based off of the tests and review quizzes before the tests. And so you basically had to do amazing on all of those to get a good grade in class. So that's a lot less stressful.
Okay, good. Well, hopefully it can be less stressful. And to be quite honest, hopefully it's a motivation, because I don't think you can do well in the test unless you do all the homework, or at least nearly all of it.
Yeah,
And-
I'm hoping to understand everything completely before walking into a test. So yeah.
Nice. All right, Timmy, let's see, you got number 33. Okay. All right, here, chapter 24, number 33.
You're going to post this video lecture later tonight, right?
Yeah, I've recorded them all, and I noticed, like the other two, as soon as I stopped, they saved to my hard drive, and then later tonight, or hopefully soon after I'm done here. But they do take a while to process to YouTube. I can send them up right away, but it'll be a couple hours before YouTube does their stuff.
Okay.
I think they scan it, and
Sounds good.
I think they look for copyrighted materials. Somebody trying
Yeah.
to post a Disney movie or something.
I'm
Oh, and then they do closed caption. Yeah.
okay. I've been doing physics all day, so I'm going to take a mental break. So I hope everyone has a good weekend.
All right. You too. Technically, it's a 3-day weekend, but
All my
Don't go
classes are
anywhere.
asynchronous anyway.
I know it's like every day's the same, and
Mm,
you don't want
Yeah.
to get in big groups and get some fatal disease.
well, have a good weekend, guys.
All right, you too.
Did you do the pizza problem already, or are we gonna do that
Oh, I
towards
did
the end?
not. Can we do the pizza problem?
I would love to.
Yeah, I've been wanting to do that because I wanted someone to post it back up here or share a screen. Can you want to share your screen again?
I got it.
Okay, let me stop sharing mine. There we go. I think I got it. Okay, you should be able to share now.
Okay.
Oh, that's helpful too. I begin to see where his problems are. Okay. So let's see if I can understand the question. A large pizza's radius is bigger than a small one. Okay, by, and we don't have a number. We just have a P percentage.
Yes.
Okay, so let me draw a small pizza. Don't lose it yet. I'll kick
All
you
right,
off, okay?
Yeah. I'll
Yeah, wait for me to kick you off. Okay, so I'm just going to draw 2 circles, and then later on you'll see them. Okay, and I'm going to put P. Looks like a sub R percentage. the large pizza's area and also its price is bigger than the small one's area by, let me just write that number down, 79.4%. Now, help me out here. Again, I don't see a question.
Yeah, so we're solving PR. So the question's technically right here. The red mark, you see the red PR at the bottom right?
Oh, yeah?
That just tells you what you're solving for.
So the question is solve for PR. Okay,
Yes.
gotcha. Okay, so let me go back to my camera phone here. And then go back to the phone here and do a screen share. Click on laptop. Okay. Nice. Okay, so here's what I drew while I was reading that. Okay, so I've got two pizzas here for discussion. Let me call this R1. That's going to be the radius of the small pizza. And let me call this R2. Now, I don't know if this is completely true in the business world, but I think this problem was implying that not only is the area bigger, but the price is bigger. And I think it's trying to imply that the price per square inch or square centimeters, whether you get a small one or a big one, are the same.
Mm-hmm.
And I think we need that. I don't think there's anything we can solve that. So in other words, there's no discount in buying a bigger pizza. Or there's no penalty in buying a bigger pizza, at least per bite. You know, one bite of pizza is the same. I think they're saying. Okay.
He also gave us something to fill out. It's I think it's FR equals 1 plus PR over 100, and like that he gave us that equation, I'm pretty sure, and that's how you solve this one, but I wasn't sure how to get FR.
Okay, say that again. FR
equals 1 plus PR divided by 100.
Oh, okay. I
think FR is a scaling factor.
Okay. Okay. All right. Now, I lost the question, but could you help me again? This piece of R was how much bigger
The
radius was?
Yeah, the radius.
Okay, so I should, to remind me, I'm going to put the word radius here. And this one right here, the 79 is how much bigger the area is, right?
Yes.
Okay. Okay, so, all right. So let's do this. Let's call the bigger one area 2 and the smaller one area 1, okay?
Mm-hmm.
All right. So, area 2 would be bigger than area 1 by 79%. And I think this was the equation you were talking about. So in other words, area 2 would be area 1 plus 79.4% of area 1. Does that make sense?
Yes. Yeah.
So if you factor out area 1, you get that. And that would be, I think you were reading something about 1 plus the bigger factor or something.
Yeah, I said the scaling factor equals 1 plus PR over 100.
Okay. Okay. So so this is my equation, if you will, for how much bigger the area is.
Mm-hmm.
Okay? But we're asked to find how much bigger the radius is. Okay. So let's talk about the area of pizza pie.
Do we use pi r squared for this?
Yeah, pi r squared of number 2. And let me just put this together as 1.794. And then this would be pi r1 squared. There's a pi on each side, so I'll get rid of those. But here's the magical step. To get radius number 2, I would take the square root. And this would give me that factor of how much bigger the radius is. So if I grab my calculator and go the square root of 1.794, I would get 1 point, and maybe I should do 3 decimals. And so this would be written as 1 plus, and I'll write it as 0.339 times radius 1. That's the percentage, 33.9% bigger. And I think that is, if I understood your notation or his notation, that is how much bigger, the percent or bigger the radius is.
Huh.
And it's all because of this square factor.
Yeah, that makes sense. I guess I'm wondering what I did wrong when I tried it out. I think I see it. I think I left my percentage as a percentage instead of putting the decimal. I didn't do 0.794. I think I just did 79.4. Okay.
Ah, yeah, okay, yeah, now of course that's a big thing. Make sure a percentage, you know, when you start doing math, is a decimal. You got to change it into its fractional form.
Right, because it's over 100. Yeah, that was a silly mistake. All right, well, yeah, that makes sense. Thank you.
Okay, great. Now I think I started to list for Timmy here, number 33. So I'll go back to that. Good. Let me find number 33. Oops, wrong class. 33. A long, straight metal rod has a radius of 5 and a charge per unit length of, find the electric field at 3, at 10, at 100, where the distance are measured perpendicular. All right. Well, let me point out that A, being 3 centimeters, is less than the 5 centimeters of the metal rod. So if I were to draw a picture here of the metal rod, 3 centimeters out would be something like this, because the whole radius is 5. So we're still inside the metal rod. A metal rod is a conductor. The field inside a conductor is 0. So there's A. What is the field at 3 centimeters? 0. In fact, the field would equal 0 from R, anytime R is less than 5 centimeters. So anything less than 5 centimeters, I'm just going to put 0. And so A is 0, B is not.
So so does it matter if it's saying that the charge is on the surface or inside?
Well, once they say it's metal, they've said it's a conductor, and this charge can only be on the outside of a conductor.
So it will be on the surface.
So yeah, we know it's on the surface and we know there's no electric field on the inside.
Okay.
Yeah.
So
The,
on the surface, will we consider the two top and bottoms, or are we only gonna consider the surface?
yeah, only the surface. The key there also was they said a long wire.
Oh, okay.
So what they're really saying is don't pay any attention to that very, 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 very small amount that would be on the top and bottom of it. It's really all along the surface.
Got it. Then I have no question with this problem anymore.
Okay, good.
Yeah.
Nice. All right, and, jump back over to the Zoom. Hey, thanks, Dr. Young. Yeah, I'm sorry I butchered your name, but I'm glad you finally saw the pizza one and must have not had a microphone or something. Nice. All right. Hunter, I see a hand.
I just wanted to say thanks. I'm going to head out for the day. Appreciate all the work.
Okay, same as always. Shoot me an email anytime and keep working on these and don't work too hard at your work, yeah.
I will. All right. See you next Friday.
All right. All right, so you got two Jonas. And Timmy, any more questions for me yet, or? Hey, what's
I'm
the
gonna-
time, anyways? Oh,
I'm gonna.
no,
It's 4:25.
we're getting close to our 4:30. Okay.
Oh, thank you for the help. I'm gonna head out now.
Okay.
Appreciate it.
Yeah. You are welcome. Let's see if there's any important emails here. Looks like I got a couple of questions by email. I'll do those when we log off here. Yeah, looks like there's 4 questions. Oh, good. Well, if the two of you don't have any more questions, maybe I will call it good for the day and say, hey, don't hesitate to send anything by email.
Sounds good.
And I'll put up these recordings. You guys, since you saw it, you probably don't want to see the recordings, or maybe there was something in an earlier one, but yeah. All right. Well, you guys have a good weekend. I guess technically it's a holiday one, but in this kind of weird world we live in, I personally, for me, I don't know what day is what. It doesn't really matter. Monday's the same as a Tuesday, same as a Sunday.
As long as it's not exam day.
Well, yeah, good point. Yeah, you will start to have a schedule of exam days. Yeah, so that'll be a stressful day. Yeah.
Well, have a great weekend then.
All right. You too. Take care.